All right, good afternoon, colleagues, and once again, welcome to our webinar series looking at longitudinal data. This is part of our quantitative webinar series for the Center of Excellence in Human Development. And thank you for being with us for the past four webinars that this is the fourth one. So you've been with us for for a while, and we're grateful that you have joined us. So today we're doing the last bit of this series. And just as a reminder, these webinars are recorded and they'll be stored as a learning resource for the Center of Excellence in Human Development. But we request that if you've got any questions, that you use the Q&A session or the Q&A box or the Q&A tab on your Zoom platform. And also feel free to unmute your mic at the end of the presentation to ask any questions. And this is the last one, so this is the second part of the longitudinal data analysis. So we're getting into the actual analysis. And there is a toolkit that has been provided, that will be provided to everyone that has attended. I've shown you the scripts, and I will also show you today some of the commands in Stata as opposed to R. And today, the last bit that we are looking at is looking at regression as an introduction into understanding associations or exploring associations between variables, and also how we then analyze longitudinal data. Now, just as an introduction in terms of why one might want to assess or to apply longitudinal data analysis methods. Often in research, whether you're looking at life course epidemiology or you're looking at any other field, whether it is in the social sciences or even in other economic sciences, one is always interested in understanding relationships between variables, because those relationships help us to understand, how one phenomenon is influenced by some conditions or by some factors. And in the sense of epidemiology, we may also be interested in understanding whether one phenomenon causes another phenomenon. And so assessing these associations helps us to see whether there's a relationship between particular variables. And an example in life course epidemiology would be, for example, a researcher was interested in assessing whether there's a relationship between birth weight and changes in body composition. So what that means is if a child is born, for example, small or appropriate or large for gestational age, how does that influence the child's trajectories in accumulating weight over time between the ages of birth up to 10 years, for example? And an example of that type of a study could be, for example, where you've collected data from birth right up to the age of 10 years, and you've collected some weight data, some height data. You've computed BMI from the age of 2 years. You've collected some feeding practices, such as, for example, formula feeding versus breastfeeding, and you've collected the age of the child in months. And so you're interested in testing a hypothesis whether the differences in sex, whether there are differences in sex and feeding practices, and whether there'll be differences rather in body composition in relation to sex, feeding practices, as well as birth weight. All right. And it may be because you've identified a problem in your particular field. And in this particular example, there's a concept of pediatric obesity, which is rising. And therefore, as scientists in this particular field, we're interested in understanding what are the factors that drive these patterns in pediatric obesity. And so one of the first and probably most common methods that people use in trying to understand these relationships is what we call linear regression. So you have simple linear regression where you're interested, for example, in understanding one outcome variable and how it one independent variable and how it influences a dependent variable. So here, for example, and that relationship is represented by this equation that we see here on the screen. And if you think back to your high school mathematics, if you think back to the function for a linear equation where I think it's y is equal to mx plus c, that represents, the relationship between x and y. And what we're trying to capture in this equation is to estimate some parameters that help us to understand the relationship between the independent variable, which is your x, as well as the dependent variable, which is your y. In some text, this can be called maybe the outcome variable, which is your independent variable, and this may be called the exposure variable, all right? So there are different terminologies which are used in the text, but they all mean the same thing, all right? So you're interested in one particular outcome, and an example is in our particular case, you're interested in understanding patterns in pediatric body composition. So whether you're measuring it by BMI or you're measuring it by fat mass. And so that is your outcome of interest. And it is influenced by some factors that you are yet to establish. And say, for example, you, based on literature that has already been published, you understand that feeding practices will influence that outcome. So you add in your data collection sheet, you're interested also in collecting your feeding practices as we showed earlier. But also you know that age is a factor, so body composition will increase with age. So if your independent variable here will be your age, for example, we know that age influences your body composition, but body composition does not influence age, all right? And so you're interested in understanding how the relationship, what the relationship between age and body composition is like, all right? And you've got two parameters that will help you to explain that. One, it will give you, one is a slope, which tells you, for example, the magnitude of increase in your dependent variable with every unit increase in your x variable or in your independent variable. So how much does a unit increase in age? How much increase does it cause in your dependent variable in this particular case, which is your body composition? And if you were to set x at 0, this value here tells you what the value of y will be, and this is called an intercept. So this is the value of the outcome variable at the start, meaning where x is equal to 0. All right. Now, in your data set, you've got observed variables, which are your x variable as well as your y variable. So this will be your age and your weight, and you may have other, as I showed at the beginning of this lecture, you've got other variables which are other x variables or other independent variables. Your feeding practices, for example, will be an independent variable. If you think about exercise, for example, whether a child is engaged in any form of physical activity, that will be another independent variable. So you can have more than one independent variable. And if you only have one independent variable, that is called simple linear regression. If you've got two or more independent variables, that is what we call multiple linear regression. I know many people use different terminologies, and they will use multivariate linear regression and so on. Generally, even though you're dealing with multiple variables, if you're dealing with multivariate, usually it is when you've got more than one outcome variable. In this particular case, we're only dealing with one outcome variable. And this outcome variable that we're dealing with here, as explained in previous lectures, we're mainly focusing on a continuous variable. If you're interested in a different type of variable, as explained yesterday, the different types of variables, if you've got a nominal variable or a binary variable, for example, you are dealing with logistic regression where you're interested in a presence or an absence of an event. All right. So here the estimates of the intercept and the slope are estimated using something called ordinary least squares, and that is a process to estimate exactly where, what the appropriate slope to explain the relationship of X and Y are, all right? And as I said, these coefficients, they describe the relationship between the dependent and the independent and the dependent variable. All right, but importantly, and this is very important, and I've only highlighted two here, but there are a couple of other assumptions. We're not really focusing on regression in this webinar, but we're using it as a way to introduce the concepts that are important. There are assumptions with every model that we apply. We need to understand what the assumptions are. So when I think about how I try to understand every modeling technique that I use in my in the work that I do, being someone who is not originally a statistician. So I try and understand three things. One, what is the model itself? So what is a technical model? So an example is the equation that I just showed you of a regression model. The second thing that I try to understand is what are the assumptions of that particular model? Because if you violate any of the assumptions of the model that you're using, then the results or the findings that the estimates that you're obtaining from that model may be biased. All right. So it is important to understand what are the assumptions that each model carries before you apply that particular model. All right. So here, for the purposes of today's lecture or today's webinar, where we're dealing with longitudinal data, there are two important assumptions that are important that I want to highlight. One is that the residuals must not be correlated. All right. And the second one is that, excuse me, is that the data, or rather the residuals must be normally distributed. All right. Now, the reason why it's important to understand this, to highlight this assumption is that in longitudinal data, you've got this concept of autocorrelation, which refers to the relationship between the values of the same variable at different time points. If you look, for example, at an individual that is measured a couple of times, let's say they're measured at birth, at 1 year, 2 years, and 3 years, the the measurements of each individual will be related because in other words, they will be correlated because they are from the same individual. And for individual one, there'll be a correlation between his or her own measurements. And for individual two, there'll be a correlation between his or her measurements as well. All right. So what you are then dealing with in terms of the measurements that you have in your data set, you've got variables or rather observations which are not independent, all right? Because your weight at time point 2 is influenced by the weight before, at age 2, for example, is influenced by your weight at 1 year and your weight at birth, all right? So a child's weight at age 6 is likely to be similar to to be associated, rather, to be correlated to the age at 5 years. So, children who are smaller, who are who are starting off small are likely to continue on that trajectory, and children who are starting off large are likely to continue on that trajectory, such that if you correlate in a data set weight at 6 versus weight at 5, there is a strong correlation between those two variables, meaning there's a strong linear relationship between those two variables. All right. Now, this issue of autocorrelation occurs in the context of clustered data. And there are many ways of data in which data can be clustered. All right. Data can be clustered within an individual or within a particular setting. So, for example, if you look at, if I take, for example, the example that I just gave of in a longitudinal data set where you've got a repeated measurements for each individual. So the observations of that individual are clustered within, the observation in this data set are clustered within individuals. If, for example, as in the example that I gave of a research study where we looked at children from different countries, 6 different countries, including South Africa, because children are facing similar conditions or are growing up under similar conditions, their patterns may be similar. So there may be similarities between, children in South Africa. There may be, close relationship among children from South Africa compared to children from Pakistan. In one study, for example, where I was looking at age at menarche. So menarche is the age at which girls have their first menstrual cycle. And that differs from country to country. In South Africa, the average age of menarche is around 12 years. So children have their first menstrual cycle from around the age of 12 years, for example. In another country, and I think this was in Guatemala, the average age was 14 years. All right. So clearly there are differences in terms of the average age or in terms of the outcome between the different contexts. All right. And so context is very important in terms of influencing growth and developmental outcomes. So that clustering then happens within a context. All right. So you need to make sure that you account for this relationship or this correlation that can occur between in observations from each country. All right, and so the reason why it's important to take this into consideration is because the estimates that you are obtaining from this relationship or from these modules may be biased, and therefore you may make incorrect statistical inferences. And this just demonstrates an example of how data are clustered. So, and this is why we're talking about multi-level modeling or mixed, in terms of, for example, mixed effects modeling. So we've got different levels in which data are clustered. Here we've got your observations at level 1. You've got the individuals. Also, this will be that if you are dealing with children, these will be the different children that are sampled in your data set. So the observations are clustered within each child, and the children themselves are clustered within a particular location. It can be a country, as the example that I gave earlier, or it can be whatever locality. It can be a city or even a school. All right. I mean, this happens a lot in studies where you're comparing performance at school. And so you've got children within a particular classroom who are taught by a particular teacher compared to a different school where the teacher is different. And so that may influence the outcomes of the children in whatever measure that you're interested in. So it is important to account for those differences in the environments in which those children are being taught. All right. Now, what we see here is that the data have got a hierarchical structure in which observations are nested within individuals and individuals are nested within different locations. And children from different settings, therefore, may experience a similar environmental factors, all right? And now, one of the things about these that is useful to consider when you want to look at these relationships is whether you've got equal or unequal observations in your data set. If we think back, for example, to regression, what regression does is that it will only run your regression analysis for the individuals who have measurements, who've got a balanced data set, all right? So you must have equal number of Y and X variables. Whereas in when you're dealing with, usually when you're dealing with longitudinal studies, you always, without fail, most likely are going to have some individuals who have missed some visits and therefore will not have data for those particular visits. So you will have an unequal number of observations between the children. If, for example, you are measuring children at 5 different, or let's say at 10 different time points, you may have some children who've got measurements at for only 5 time points. Some will have for the full visit, and others will only have a 2 or 3. Now, we need to have models that are able to handle those challenges that we experience in the data. All right. So the two challenges that we're dealing with here is one, this hierarchical structure of the data, and also the fact that you've got unequal observations in the data set that we are dealing with. All right. So it goes back to what I was saying earlier in the past webinars, that we must, the start of every analytical process is the exploration of the data, all right? So you will be able to see in your data set whether there are unequal observations or not, all right? Now, generally, what these models do, all right, is that they want to run and handle these challenges at the same time, and the model can be separated into two parts. The first part is what you see here. So if you're just, I mean, it's similar to the linear regression model that I showed you earlier. All right. So what you have here is the outcome variable, which is, say, for example, this will be your body composition. All right. For the child I, now we use these subscripts, all right, to identify the number of the child. All right. So the I subscript represents a child, and J represents a time point in the in your study. All right. So you may have measured at the for 6 time points. So if at the for the first child at the first time point, this will represent the weight at for the first child. This will be 1 weight 1, which represents the weight of the first child at the first time point, all right? And weight 1, 2 represents the weight or body composition side. If we say BMI, for example, BMI of child 1 at time point 2, and so on. Similarly, with the independent variable, which is your X variable, all right, you've got the measurement at time point for one individual at the different time points. Now, if I take you back to the structure of longitudinal data, these are time varying variables, all right? So they will change for every child. They will change over time, all right? They're different for every child and different between time points. And so this is the error term, which explains the variance that is not explained by this model, all right, which gives a insight into the variance that is not explained by this model. Now, what these models do is that they break, there's a way of estimating these parameters here, your beta 0 and your beta your B0 and your B1 for in this particular case, all right? And there is a model that includes both the fixed effects as well as the random effects. Now, what these models do, just to explain slightly what that means. All right, so you've got they first estimate, what the average or what the estimates are at a population level. So what is the average growth over time? All right. What is the average BMI over time? So that's a population level estimate. It does not account for the individual variations. Every child will have their own pattern over time. All right. But we are interested first, we're also interested in understanding what is the average growth curve or what is the average pattern over time for this particular population. All right. And that will help us to compare population 1 to population 2, for example. All right. So we estimate the intercept at a population level, and we also estimate the slope at a population, but it also allows for individual variation. All right. So every individual will vary from the mean curve. Every individual will have some level of variation in terms of both the intercept. We won't all start off at the same point, all right? And we are not all going to have similar trajectories. So some individuals will have faster growth, in comparison to the mean curve, while some individuals will have slower growth in comparison to the mean curve. Some individuals may start off higher than the average intercept or the population mean, and some individuals may start off lower compared to the population mean. So these models, these mixed effects models, they take that into account. And so what then you can do is, if you look at this model here, you can then replace this B0 and B1 with these terms that are here in the expanded equation. All right. So generally, what these models do is that they decompose the key components. They decompose the data into two key components, and those are your fixed effects as well as your random effects. Now, as I said earlier, the fixed effects give an indication of the average pattern in the population. What is the average growth curve in that particular population? Whereas the random effects, they tell us how every individual deviates from that normal, or not normal rather, from that mean, from that average curve, all right? And together these are called mixed effects modeling. I mentioned earlier that linear regression, the estimates, your beta coefficients are estimated using what is called the ordinary least squares. Here, the estimation that is used is called maximum likelihood, or there's also restricted maximum likelihood, which is an estimation after accounting for the fixed effects. All right, now an example here is, for example, if you are interested in looking at the weight of a child, and looking at the relationship between weight of a child and also accounting for the biological sex of the child. All right, this is what the model would look like. This is what the fixed model would look like. But also you also need to account for the deviation, for example, for the individual variation in the intercept and as well as the individual variation in the slope. And this is now a full model that accounts for both the fixed effects as well as the as a random effects. All right. So as I've explained earlier, individuals are allowed to have their own slopes, and they're allowed to have their own intercepts in this type of modeling. Now, as I said earlier, it is very important to understand what are the diagnostics, or rather, what are the assumptions of this model. All right. Now, you have in literature both linear mixed effects as well as non-linear mixed effects modeling. Usually in growth data, which is the examples that I was talking about earlier, you are usually dealing with nonlinear data. If you look at the growth curve, for example, you have more of a sigmoidal shape. It's more of like an S shape where you've got fast growth in the early years, and then it tapers off to a slow growth in the childhood period between 5 and say about 11 years, which is the pre-adolescent period. And then again, you experience another sharp rise in the adolescent period, which is between the ages of, say, 12 up to the age of, say, 16, 17, where the growth curve will then again plateau. So that relationship is not a relationship that can be um, estimated with a linear model. All right. And you can think of a relationship in your particular scenario. And this goes back again. I'm going to keep referring to what we spoke about earlier, where you are supposed to explore your data. You can explore your data using your scatter plots, the line graphs that I demonstrated to you, your growth plots, and so on. All right. And those will give you an indication rather of the pattern of the relationship, whether this relationship is a linear relationship or it is not a linear relationship. The next important assumption is that these clusters are independent. If you're looking at individuals, for example, these are individuals from different families. If you're looking at children, for example, they are from different families, because for example, that children from within a particular there is a correlation in terms of factors or of outcomes among children from the same household. So children from household B, for example, may be taller compared to children from household A. So you want that level, and if you in some studies are twin studies. All right. So, and you know that, I mean, especially when you're dealing with identical twins, you are likely to have very similar characteristics. All right. So you want the clusters to be independent. So if you're dealing with, schools, you want to measure from school A versus school B. All right. So that is very important, as well as um, normal random effects as well as normal residuals. And these are things that you can, test once you have, and it's very important to do this post hoc test. After running your regression model, it is important to check, the distribution of your residual of your residuals, and to see whether they've got a homogeneous variance, which is this term here, that is which is homoscedasticity, as well as to check whether they are normal. And you can use different types of plots. You can extract the residuals and plot them with a histogram, or you can use the QQ plot. All right. And obviously, the issue of dealing with autocorrelation, these types of models, they deal with that. All right. Now, in practice, one of the things, as I said, in terms of the steps that one is interested in, is summarizing the data and exploring the data. all right, by whatever, obviously we're dealing with longitudinal data here. So by time as well as by the different factors that one is interested in exploring relationships with, and to perform comparisons. But also importantly, so if, and when you're modeling, say, growth in children, it is important to model growth with just time on its own, all right? First of all, first and foremost, without adding any covariates. You can then adjust the model by adding the covariates to assess how these covariates influence the relationship between your age and your outcome, for example. And say, for example, if you take an example, the example that I explained earlier, that we started off rather with earlier, which is body composition changes over time. You start off with age versus rather with body composition versus age, and you model that relationship, and then you can model, you know, you can then adjust the model for, if you want to see whether there's an influence of biological sex on that relationship, because we know that there are, for example, differences between boy children and girl children in terms of body composition. And so we want to account for that and want the model to demonstrate that if we are assessing patterns. And so in summary, longitudinal data is one of the things that we're looking for, is to account for this individual variation or within individual change, but also we're interested in looking at differences between individuals, and also importantly, the average curve. And models such as your mixed effects modeling can achieve this at the same time. They can achieve both at the same time, by simultaneously modeling both the within individual change as well as heterogeneity. And the distinction between within individual and between individual differences is really what we are interested in longitudinal data modeling. So this is just some references, two references that you can access to try and understand more about longitudinal data modeling. The second one is available online. If you go to this UCLA website, and you will have this. This one is a book. So if you search for this book, and I love this book because it helps, it's quite straightforward and is simplified, and has also technical detail to help the non-statistical reader or to understand what these models are. So this is the end of the presentation. What I'm going to do at this moment is to go into an example, a practical example, and I want to start off with a data set. All right. So I'm going to open. I've stored my data or my tools in or rather the commands. I've stored them in a do file. All right. And when I open that do file, so I'm going to update next when I open Stata. This is what the do file looks like. And again, so I'm going to create data from scratch. And we're going to demonstrate what happens when we when we run these command lines. I'm trying to look for the. Okay, I don't think this is going to help me if I've got everything. I need to, okay. I can't have this in full view. I must have it in, I'm going to just move it slightly to this side so that you can see what comes out. Just a quick orientation on Stata for those of you who are not familiar with Stata. again, we're dealing here with an interface that helps you, to run commands, but also to view the variables that you see here. Here, you've got your history window, which shows you the commands that you have run, even the ones where you experience an error, they will show here, as you will see. And here you've got the window that that describes the version of your data and some as well as your uh, administrative details, but also the results are going to show in this window here. All right. Here you've got your command line. This is where you run your stata commands. As you will see, I'm going to run them from a do file, but if, for example, I wanted to run some command, for example, if I wanted to, there's a data set within Stata which is called auto. If I wanted to use that, I can run the command here, sysuse auto, and it's going to call that data set. All right, here's the data set. As you can see here, I've got variable names, and here I've got the property.
Your screen is not showing.
Oh, did I stop sharing? I'm still sharing. Oh, okay. I think I didn't share entire. I shared um I did share entire screen. Can you see my screen now?
Yeah, we can see it now.
All right. Thank you, Humosa. All right. Okay. Let me a quick rerun of what I was saying earlier. So this is what Stata looks like for those of you who are not familiar with Stata. You've got a couple of windows that offer different information about the session that you're running, but also about the data that you have in your session. All right. So here you've got the history, which shows you the history of the commands that you have used in your data set. And here you've got the command line. This is where you run your commands. And I was showing an example earlier. I'm going to run clear now to clear the data. But now, for example, if I wanted to run a command for using this data set that exists, this system data set that exists within Stata, I use the command sysuse, and the data set name is auto, and it's going to give me that data set. All right. So I run it here, and as you can see here, the commands that I have run appear in this line here, and the results of my actions appear here. But this is not the data set that we're going to use. So I'm going to clear that. And we're going to be running from this do file. So this do file, this is where you store all the actions that you are performing in your analysis, both in terms of your data management as well as your analysis. And even similarly to an R script, you're able to add your notes here. If you add a forward slash or if you add a star, it will recognize that as a note and not as a command. So here I'm going to generate a few variables. I mean, yeah, I'm going to generate a few observations and variables. And to do that in Stata, in R, I would simply click here and put the cursor at the beginning and click run. But here you must highlight and then click the do button. And as you can see, the results are appearing there. And the action, though here, the action is hidden because it's in a do file. All right. And so I'm going to generate weight at different time points. And I'm sure there's a much easier way of doing this for people who are into coding, but I'm not a coder. I'm a lowly scientist, so but who's into quantitative. So I use a much longer method of generating the data that I'm generating. All right, I've generated weight there. All right, and here I can summarize my weight by sex of the child. All right, I've got boys and girls in my data set. And before, in fact, I do that, let me just show you the view of what the data look like. This is editor, this is view. No, okay, where is it? No, okay, cancel. All right, so this is what my data look like. This is sort of like similar to a spreadsheet, an Excel spreadsheet. So this is the data frame in its data, and you've got the ID of the individual, you've got the biological sex, you've got the weight at different time points from birth right up to 24 months. All right. And now I want you to notice that the variable sex um, is the color scheme is different to the rest of the variables. So the numeric variables will generally be black will be black in Stata, but your string variables will be, I'm not sure, I think this is burgundy, will be a burgundy color, sort of a red color. All right. Now you are unable to use this variable in some statistical analysis until you make it a factor variable. All right. And I'm going to show you how you do that later on. So running the data from a do file. Okay, so I can summarize the data by sex, and it's going to show me the results here. You can see what the descriptive statistics look like at the different ages. And I'm sure even here with data, there's a way that this can be generated one time into a single table, which is what I showed you in R. All right. So you can see the weights of the different individuals at different time points. All right. Now, this data, I mentioned that you can have data in wide or in long format. All right, you can have longitudinal data in both the wide and the long format. And if I just show you again the data that we're dealing with, you've got the data of child one. You've got all the weights of child one in one row. Okay, so all the data pertaining to this child, including their sex, is in one row. All right, but this is not useful for us when we want to perform longitudinal data. All right, so there's something called reshape, which is part of the data management process that you will undertake. And here is a simple command, reshape, and you want to reshape to long. So you specify, this is an argument, all right, and you specify the variables that you want to reshape, and you must specify the ID variable as well as the time variable, all right? So whatever you've named it, in my data set, so this will go into a variable called time. It does not currently exist in my data set, but if you look at this, if I go back, if you look at the data, the weight at 0 is called weight underscore 0, weight at 3 months, weight underscore 3, and so on. So what I'm telling Stata, which is similar to what you would find in R, is that it must take this value and must create a new variable called visit, and all of these values will be then aligned to visit 0, for example, and these will be assigned to visit 3, assigned to visit 6, and so on, 6 months and so on. So these are months. Okay, let me minimize that. So how to do that? And again, so I've added, so here in this script, I've intentionally left out certain things which will result in an error when I run them, just to emphasize certain points. All right. So, and this is what I'm going to, as an example, this is what you're going to experience now. Now, if you try to reshape this data, um, it's going to give an error. All right. And the reason why it gives an error is because of how, Stata does not recognize the, you know, the value that I want to add to this visit variable here. All right. So, and this is important when you're dealing with data, and when you're naming data, whether you are naming them in your RedCap, or you've been using R and you want to then save your data you want to save data to Stata, and it's important to check how you name your variables. All right. So here the next thing that I need to do here is to remove this underscore and keep and make sure that there's no space between the number that I want to include in the visit as well as the variable name. So it's going to take all the weight variables and include them under one variable called weight. So let me run that, and then you're going to see what happens. So I'm renaming these variables, and as you can see, that is the result. The variables have been renamed. Now, if I run this reshape command, it runs and it gives me positive results that it has accomplished what I asked it to accomplish. If I wanted to reshape to wide, go back to the wide variable, here the argument would be wide. But here, I've added the argument long because I want to convert this data to a long format. Now, I want you to observe here. Initially, we had multiple variables. We only had ID, sex, weight 0, weight 3, weight 6, and so on up to 24 months. Whereas now, all the weights, which were initially in different variables, are all now in one variable. They're all included in one variable. And if we now look at our data set, we can see that each child has got multiple rows. The data for each child occupy multiple rows. All right, you've got data at time 0, at 3 months, and so on. All right, and here obviously the sex of the child does not change, but the weight of the child changes from birth up to 24 months. All right. So this is what the data look like now. All right, and so the next thing that you want to do, so we've reshaped. All right, now in Stata, to see certain characteristics of the data to describe the data, for example, you must you can use there are certain commands that you use to describe. So, and this one is going to run an error. It's going to give an error as well, and you'll see why. The reason why it's giving error is because I have not specified to Stata that my data are a panel data, all right, or no, a time series data. So you need to specify that to Stata, all right? And to do that, you use this command xtset and you specify the ID of the child as well as the time variable, all right? So if I run that, it now recognizes this data as longitudinal data. And if I describe, it's going to then tell me, that, yeah, it's going to give me descriptions about this data set, all right, and tells me that I've got a complete data set. Then, I mean, like I showed you earlier, I don't want to run this again. I mean, this is just an alternative. I did say that I'll provide an alternative to R where possible. These are just some ways of visualizing your data in Stata. So this should generate a scatter plot. It is running and it's taking time and it's appearing in a new window. All right, so these are individually. All right, so you can see the pattern of each child, and similarly, you can generate. So this is still again scatter. Okay. All right, so this is something similar. All right, I thought I added a different command to show. All right, let's see. All right, I'm going to run this one. Let's have a look at here. All right. Okay, this is still the same, but I mean, you're able to run, compare your weight and your visit by just simply running your scatter. Let's see if I put it in the command there. Weight visit. All right, this one now is not individual. It is for the whole sample. All right, and you can see the pattern. There's sort of a curve a curvature in the data set. All right, in the pattern. Now I'm going to skip these ones here. Now that we have explored our data, you can also explore them using a stem and leaf plot. Did I add a? I don't think I added a box plot. All right. All right, so let me just run this here. All right, so now what I've done is generate individual lines for every individual, like I showed you in the in R. But now we're interested in looking at relationships. Okay, so the first model that we run is generally so in terms of best practice. All right, so it's always good to start off with an intercept only model. All right, so you're just estimating the starting point for each child, and you specify. So the syntax here is that you want this part here specifies the variable that will be used to generate your random effects. Now, remember, your random effects are the effects that allow individuals to vary from the mean. All right. So here I've specified that these estimates must vary by ID. So each child, this particular child, must have their own pattern. All right. And you can add here, if, for example, you had another layer, say, for example, a school, you wanted to vary within school and within individuals and within a particular setting, then you could add that here as well. If I run that, it's going to give the results, and you can see there it only shows results for the intercept. All right, you've got the coefficient, you've got the standard error, you've got the test statistic, you've got the p-value, and you've got the confidence interval. And the p-value tells us that this is significant. And here, the last part tells you about the variance of the random effect parameters. So the variance of the intercept and the variance of the residuals. So is the variation when you're looking at individuals, is the variation at the intercept between how much do the starting points or the intercepts differ, and how much do the curves of the individuals differ? All right, so that was an intercept model only. So now here, I'm also interested in adding a slope. All right, now you can see that you've got additional output. Before you only had your constant, which is your intercept, whereas now you also have your explanatory variable or your independent variable. And this value here, the 0.31, tells you the magnitude of increase in your y variable or in your outcome variable with every unit increase in your independent variable. So when X, which is your visit, increases by 1 from, say, 0 to 3 months, you've got an average of 0.3, this is weight, kilograms increase in the weight of the child. Let's just check, what was the weight in kilograms, or was it in grams? So it is in kilograms, right? So you've got an average of 0.3 kilograms, 0.3 kilogram increase in weight with every increase with every increase in the visit, all right, with every additional increase uh, in your explanatory variable. And again, it tells you that this relationship is, statistically significant. So if your p-value is less, if you're testing at the 5% level of significance, this relationship, your p-value, if it is less than 0.05, then obviously you are dealing with a significant relationship. And what this is telling us here is that there is a significant increase in weight with an increase with time, as time changes. All right. Generally, this is what you will present in your report, or in your paper, because this is what we interpret in terms of, at the end of the day, we're interested in understanding, in interpreting the relationship between your outcome variable and your exposure, or your independent variable. These are important because you want to account for them, but ultimately this is what you're interested in. To If you had other variables, explanatory variables, you would see that relationship, or you see their relationship with the outcome variable also in this particular table. All right. Now I'm going to demonstrate what it looks like in R, and then we're going to end it here for today. All right. So here again, with R, I'm using a different data set. We're using this lemma function in R, and we're using the data set called observations, and we're looking at height. All right. And again, you run an intercept only model. All right. And here I mentioned that, the random and fixed effects are estimated using your maximum likelihood or your restricted maximum likelihood. And here you're specifying that you want to use your restricted maximum likelihood. And you can run your model, and to see the summaries of the model. All right. Here, it does not give an actual p-value, but it gives you a level of an indication of significance using these stars. All right. So you can see that star, if you've got 3 or more stars, it is extremely significant. If you've got 2 stars, it's less than 0.001. 1 star is less than 0.01. And if it's less than 0.05, it only gives a dot. All right, you'll see a dot here instead of a star, and that tells you that it is significant. All right. You can also run now with your age variable. Okay, let's see what that model looks like. And there we go. Okay, so this one tells you that, okay, again, there is a significant increase in height with age, and it is highly significant. And being a girl child is associated with shorter height compared to a boy child over time. All right. So this is basically how you would set up your your model. And let me see, I didn't run, I didn't check add a comparison of models, because that's one of the things that you want to do in your model in setting up your models. You want to compare, whether your model improves with adding these explanatory variables or these independent variables. So I'm going to compare your first model to the second model, and I think it's BIC. I hope I get this right. All right, BIC, MO, and M1. Let's see. Yeah, okay. It has run. Okay, so this is the Bayesian information criterion, and so a lower value here indicates a better model. So you want this value to be lower. So clearly you can see here your first model, which includes these explanatory variables. It includes your age. In fact, let's see what will happen if I don't add age, sex there. Let's just run another model. I'll call this one model 2. No, let's call this model 1. Yeah, let's do model 1. In fact, I want to have it before this one. And I'm going to have this one as model 2. And I've got, oh, what is it, sex? Okay. Yeah, it's called sex. Again, I'm not sure if I did mention this. So the random effects is specified here in this argument here. All right. I need to remove that and add sex plus. Okay. Let's run that and see what it does. Okay. Summary of model 1. Okay, so this only has age now. You can see that age is positively associated, meaning with increase in age, there's an increase in height. If it was negatively associated, it would mean, if there was a negative here, for example, it would mean that with an increase in age, there's a decrease in your outcome variable. But we can see this one is positive. Now let me run, so I've got 3 models now, M2. Let me run the second model. I need to remove that. So this is the equation. The equation is that I am regressing height on these independent variables. If I run that, it does run. And again, so this is what we saw earlier, with height being positively associated, but being a girl child with being associated with shorter height compared to boys. Now let's compare and see, which of these is a better model. All right. So what this shows is that, okay, obviously adding covariates to your model improves the model. Adding independent variables, rather, in other words, to your model improves the model. It changed, the BIC changed from 3,156 to 2,284. And there's also a slight improvement when I add the sex variable. So which means that the addition of this variable explains, assists the model to explain more variance in the outcome variable. So this is how we set up, and obviously you're going to apply this in your own data, and you're going to explore what it looks like for your own data. But this is basically what the structure looks like. And I didn't go into all the details, but that's basically how we approach this longitudinal data modeling. And yeah, thank you so much for sticking around, and see you in the next webinar session on quantitative data, which will be announced at the right time. Thank you so much. Have a good day.